Alrighty, good morning, gang. Welcome back to College Algebra. I want to take a second to kind of show you a few things in Canvas, so everybody is aware and comfortable with how to go about these kind of pre-exam type things we're going to do. First thing, the activity for today. We mentioned that we're going to do a little in-class activity today. We are. The activity for today can be downloaded. It was attached to the announcement that you use to follow this this link here to come to class. If you haven't yet, please just go ahead and right-click or whatever, save as this this PDF somewhere on your computer. Later in the class, we're gonna split up into breakout rooms like we did for activity 1, and then we'll knock that guy out. The other thing I wanted to show you guys, for this class, I don't use Canvas a lot because the department requires us to keep a grade book in my math lab for college algebra. I figure it's simpler just to do everything in one place. But when it comes to like getting things to you guys, Canvas is better. So the project that I talked about, little take-home project that you guys are going to work on over this weekend, you can download that here. You'll have to be logged into Canvas for this link to work. So I'm not going to like send the link in chat. So just go sign into Canvas, go to assignments, go to project 1, and this link will take you to another PDF. All right, and it looks like this. This is what I want you guys to work on over the weekend. It's a silly little thing. So what we've done here is we've got a table full of hypothetical pizzas. I think at the time, I made this last spring, and at the time these were actual prices from pizzas at like 5-star and Gumby's and shit. So you've got a 2-inch radius pizza, and then we do the calculation of that area here. The area is always pi times the square of the radius. So if the radius is 2 inches, then the area is going to be pi times 2 squared, which is pi times 4, or 4 pi. And then I list the cost over here. On problem 1, I just want you guys to fill in the area blanks. All right, so compute pi times the radius squared for each of these things. And you can leave pi as pi, right? Follow the example that I did in part A. In problem 2, I want you to calculate the unit cost. This is a really important thing if you want to be a smart shopper, if you want to be a thrifty spender in general. Rather than looking at overall prices, you should look at the price per unit of stuff you're buying, like the price per pound or the price per ounce. So what we're going to do is look at the unit cost for each of these pizzas, meaning we're going to take the price in dollars and we're going to divide by the area, the size of the pizza. Pizza is more or less two-dimensional. It's basically a circle. So we're going to look at the cost. That first pizza was $2.50, $2.5, $2.50. And we're going to divide by the area of that pizza. And that's going to give us the price per square inch, right? Or the unit cost. So the unit cost for this first pizza is 2.5 divided by 4 pi. And you can use a calculator for this. You can round to 3 decimal places, please. You'll do the same for parts B, C, and D that I did in part A there. And then in problem 3, I want you to explain which one's the best deal, which one's the worst deal, and why. We're not taking quality into account here. We're just asking which one gives us the most pizza per dollar, right? So which one is the giving us the most quantity for our money. These are important things. You want to calculate these ahead of time if you're going to be living in Gainesville, especially if you're going to be going to the bars. These calculations could save your life one day. On the next page, we're going to take the data from the first problem, right? The radius of those pizzas and their cost. All right, so each pizza up here had a radius, 2 inches, 7 inches, 9 inches, 15 inches. And it had a cost, $2.50, $12.50, and so on. You're going to fill out this table with that data. And then we're going to do some linear regression, right? So this is one of those things that always takes a little bit of getting used to. I wanted to make sure you had a little bit of extra practice with that before the test. So we're going to go ahead and run the regression algorithm on this data. So your x's are the radius, and your y's, or your outputs, are the cost. And I want to know What's the equation of the least squares line? What is the equation of the line that best fits that data? What does the slope represent? So notice I'm not asking here, what is the slope? I'm asking, what does the slope represent? Can you tell me, for example, what are the units of the slope? Is it miles per hour? Is the slope being measured in dollars? Is it being measured in, I don't know, seconds per year? What is it? What does this represent? The number R, right? That Pearson correlation coefficient, the number that tells us how linear the data is. What is R here? And what does it tell us about this data? So is this data very linear? Is it not very linear? Is it trending upwards? Is it trending downwards? What information does the correlation coefficient for this data set tell us? And then finally, I want you to use your regression line to tell me how much, what we think the cost would be for a pizza with a radius of 14 inches. I'm just not noticing this. This shouldn't be unit cost. This should, yeah, ignore this word unit. All right, here we're just looking at radius and cost. So what do we expect to be the cost of a pizza with radius of 14 inches? If you solve for unit cost here, I wouldn't take points off. But yeah, ignore this word unit. I'll fix this and re-upload the project. And then the last problem here is asking for the domain of the function that's described here and the range of the function that's described in problem 4. So again, you've made this table, and we're just making sure that you understand the concepts of domain and range for an abstract function. And then finally, what is C of 2? Is C of 2 5? Is C of 2 undefined? What is C of 2, can we say? And this is all about the function in the table. All right, so that's the project. Any questions on what you're supposed to, so I should make the instructions a little more clear. This is up now. You can work on it over the weekend. It's due on the day of the test, which is next Tuesday. Remember, next Tuesday is our exam. And you can hand this in anytime that day. What I want you to do is print it, answer the questions on the page, and then scan and submit online. If you can't print it, if it's whatever, totally impossible for you to get to a printer, I understand. Just write down the questions nice and neat on a sheet of paper and answer them yourself. But I know most of us can get to a printer. So please print and then scan after you finish it. It's due 11:59 next Tuesday. All right, now are there any questions? Yeah, let's see. No, the only sort of regression we do is linear regression. And it wouldn't make sense to do linear regression on quadratic data. So remember, regression is something that we do to a set of data, right? A collection of points. It's not something we do to an equation, but it wouldn't make sense to do linear regression on a set of data that came from a quadratic function or anything like that. Not this, we want this. Okay. So today is your guys' day. We can talk about whatever you guys want to talk about. We can solve whatever problems you guys want to solve. Our next class is the exam. That's next Tuesday. So I'm happy to do whatever you guys want to do with today. It's today the 4th, right? Jacob asked a good question. So when exactly is the test going to be open? It is during class time. I'll write this down here. You guys should write this down too. Exam 1 will be during class time because it's a synchronous class. This is how we have to do it. But I will open it and close it a few minutes extra on either side. So it'll open at 9:15 a.m. and close let's see, normally we would get out of here at 10:45, right? So I'll close it at 11 o'clock a.m. And if you look in Canvas, I posted, pretty certain I posted an announcement with some fairly detailed instructions. So please, everybody, make sure that you do read this announcement. Read it completely. Really, really important. So exam 1 next Tuesday. But this is telling you exactly how to do things for the test, and you really do need to follow these instructions. Exam will have about 15 questions. Yeah, there will be 3 or so true-false problems, 3 or so multiple-choice problems, and then the remainder will be free response problems. Kendra, can I ask what you mean by a square root example? What did you want to look at exactly there? Like solving an equation using square roots or something else? Graphing a square root function? Just need a little bit more detail. I'm sorry. So Kendra, I was asking for a little bit of clarification. Did you want to graph a square root function? Did you want to solve an equation using square roots or something else? What are we thinking there? Solving an equation using square roots? Sure. Yeah, okay. So we've seen plenty of equations like like this, right? This is an example of an equation I can solve using square roots. Sorry, the pen is a little smudgy. We can solve this equation using square roots because there is no like x term, right? There's an x squared and there are constants, but there is no just like 2x or 5x. There's no linear term. That's how we know we can solve this using square roots. And the way we do it is just by isolating the x squared and then taking square roots on both sides. So if I've got x squared plus 3 equals 12, I can isolate the x squared by subtracting 3 from both sides. 12 minus 3 is 9. And then I can take square roots on both sides. So that's the idea. If you've got x squared equals some number, then you can solve for x by taking the square root on both sides. On the left-hand side, the square root of x squared is going to be x. And on the right-hand side, when we take square roots, we'll get plus and minus, and then the square root of whatever number was there. So the square root of 9 is 3. So this is plus and minus 3. Here we got lucky because the thing that we had to take the square root of at the end was a perfect square. But that's not always going to be the case. So let's try one more where the thing we have to take the square root of here isn't quite so nice. Oh, shit. Good. All right. So first, any questions on this? We all super duper comfy with this sort of thing? Here we go. All right. Let's try something where the square root is a little bit harder to tame. let's solve x squared minus 32 equals 0. Same sort of thing. Because there is no like middle term, there is no x term here, I can solve the equation by taking square roots. To do that, I have to isolate x squared. And then I take the square root on both sides. So here I'll get x equals plus and minus the square root of 32. Now 32 is not a perfect square, right? Like 9 is 3 squared. That we call a number a perfect square if it's the square of some other integer. But yeah, 5 squared is 25, 6 squared is 36. So 32 is between two perfect squares. It's not itself a perfect square. So if I want to clean up the square root of 32, I need to factor 32 into its perfect square and non-perfect square components. So 32 can be factored a bunch of different ways. Definitely 32 is 2 times 16, right? Or it's 4 times 8. You know, we can write lots of different ways to break down 32. 8 times 4 would be the same, and then what's our next power of 2? It would be 16. This is going to be the useful one, though, right? 16 is the biggest perfect square hiding inside 32. It's true that we could write it as 4 times 8 also, but then we would have a little bit more work to do. So let me show you what I mean here. If I write this as 16 times 2, then I've got the square root of 16 times the square root of 2, and the square root of 16 is 4. So this is plus and minus 4 root 2. If we chose to write 32 as 4 times 8 instead of as 16 times 2, we could do the same thing. It's just that after popping out the 4 here as a 2, we would have to further break down the 8 as 4 times 2. So there's a bunch of different ways that people learn how to do this, like how to simplify square roots. And I encourage you to find what you like best. 32 is actually a power of 2. It's 2 to the 5. And you can always factor an integer into products of powers of primes. And that will, in general, be the procedure you need to clean up a square root. But it can also be really time consuming. And with most smaller integers, we can kind of try to think about what the largest perfect square is hiding inside there. But another way to do this, and I don't want to spend too much time here, but another way to do this, following what Jacob was saying, is I can write this as 4 times 8. And then that's the square root of 4 times the square root of 8, which is 2 times the square root of 8. But then the square root of 8 can be cleaned up more also, right? So this is equal to 2 times the square root of 4 times 2, because 8 is 4 times 2. So that's 2 times the square root of 4 times the square root of 2. And then the square root of 4 is 2. So this is 2 times the square root of 2, which is 4 root 2 again. Or if you're really feeling patient, the kind of Big Daddy way to do this is to factor this as a power of primes. This is 2 to the 5. And then I'm looking to pull out whatever the largest even number of powers is. So I can write this as 2 to the 4 times 2 to the 1. And then the square root of 2 to the 4 is 2 to the 2. So this is 2 squared times the square root of 2, or 4 square roots of 2. But I think these two are not quite as slick as this. This is a good question from Matthew. So where did the plus minus come from? When you take square roots on both sides, when you use, like, take square roots as a verb, the plus minus shows up when we take square roots on both sides. So when you kind of think of the square root as an operation that you use to solve, like adding the number to both sides or dividing both sides by some number, when you take square roots on both sides as an operation to solve equations, that's when you get a plus and minus. Okay, what else would you guys like to see? What else can we do? Can we go over the questions where you throw stuff off a building? Yeah. Does the plus minus apply to what's inside the square root, or does it apply to the number in front too? It applies to the square root as a chunk, right? So whatever this thing simplifies to, we're going to take the positive version of that and the negative version of that. Since the number here is multiplying the square root here, these are one piece. 4 root 2 is a single piece. It's a monomial. So 4 root 2 as a chunk is either positive or negative. We don't have to worry about the 4 being positive or the root 2 being negative separately from one another. It's just 4 root 2. It's one number. And as a single quantity, it is either positive or negative. So my two solutions here are x equals 4 root 2 and x equals the negative of 4 root 2. All right, the objects thrown off the building problem, those are long problems. So let me grab one of those. No, God damn it. I swear. For whatever reason, both WebAssign and Pearson have decided to like shorten the automatic timeout session, like timers, to nothing this semester. It's so frustrating. All right. Yeah, let's find one of these. I think I saw a few at the end of this. Actually, you know what? I think I have these printed here too. That would be faster, wouldn't it? Let me see what I've got here. Yeah, okay. So I think towards the end of this homework, we have again a bunch of these type problems where we're launching or throwing something. Yeah, thrown up at this velocity. So find the max height, the number of seconds it takes to hit the ground. Let's do it. We'll do a couple like this. So in this particular case, we are chucking something. Yeah, certainly homework 8 also had these. So we call it h of t equals 64t minus 32t squared. And they want to find the max height. And how long to hit the ground. Okay. So let's come back over, focus on this. I can launch Labbit. It's not there. calculator. Here it is. Never hurts to take a look at the graph of this sort of thing. So the very first thing I would do if I were you guys given a problem like this is graph the thing. So if we turn on our calculator, we can come in here to y equals, and I'm just going to put this expression in. I have to use the variable x, that's the default for the calculator, so 64, and then here's my variable button, x minus 32 times x squared. And you see right away that the window settings are not appropriate for the problem, right? I'm unable to see most of the graph, and the parts that I can see are like almost looking like vertical lines. So if I want to fix that, the reason it looks this way is because I need to zoom out vertically. I need to have a much larger y max. And I should probably zoom in a little bit horizontally. So let me change my x min to -1. Change my x max to like 6. I'll change my y min to -1. I'm not interested in negative heights here, but I need to change my y max much, much larger. Let's change it to like 150 just to start. And we'll take a look at this. All right, that 150 is more than I need. I guessed too big for my y max. And my x max is also still bigger than I need. So let's bring my x max down to 4 and bring this y max down to 50. And this should be getting close. Yeah, look at that. That's a nice picture. We can hit the trace button right here, and that will let us kind of walk around a little cursor along the graph. And this can be useful for getting approximate values that will help us check our work. So we know that, you know, here's the ball or whatever. It starts at height 0, and I chuck it up, and it's going up, 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 and it reaches its max height at around 0.9 seconds. You see the 0.968 here. That's the time. And then it starts falling, 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 falling. And when the y value gets to 0, that's when this thing is going to hit the ground. Now here y is 4, 0.5, 1.3, and then negative. So somewhere around 1.9 or 2 seconds is when this thing is going to hit the ground. And somewhere around 1 second or 0.9 seconds is when it's going to reach its max height. That max height looks like it's somewhere around 30, 32. But let's see if we can't figure these things out using algebra and see if they agree with what appears to be the case from the calculator. Looking at the picture, what geometric feature of the graph am I looking for to determine the max height? Yeah, max height comes from the vertex. The vertex is h comma k. Which one of these is the max height? H or k? Good. K, remember the output for this function, the y values, those are the heights. So k is the max height. What is h? If the max height itself is k, then what does h represent? Good, very good. It's the time when the object reaches the max height. Beautiful. All right. So I want k. How do I find k? Because this problem didn't ask when does it reach the max height, it asks what is the max height. Good. We'll use the formula for the time, little h here, and then we're going to plug that into my function to find k. I'm going to change the height function to a capital H because I don't want to confuse it with the little h down here. Okay, first we find little h, which is always negative b over 2a, which is negative. Well, what is 0, or sorry, what is b here? What are my a, b, and c for this height function, capital H? Yeah, good. B is 64, A is negative 32, and C is 0. So negative B over 2A is negative 64 over 2 times negative 32. Isn't that funny? So 2 times 32 is 64, and you've got a negative here and a negative here. So this is going to be 64 over 64. It'll be positive altogether, which is 1. So the thing reaches its max height. They're not asking for this right now, but if they were, the thing reaches its max height 1 second after being thrown. And the max height itself, I take this time and I plug it into this function. That's k. K is the output from your function when you plug in little h. Little h here was 1. So this is 64 times 1 minus 32 times 1 squared, which is 64 minus 32, which is 32. So the max height is 32. 32 what? Feet, miles, years, dollars, cats? This is 32 light years? 32 nanometers? 32 Planck lengths? Yeah, feet. Pay attention to the units. I'll tell you this, guys, I'm not a super stickler for units, but the department final for this class really is. Pay attention to your units. All right, part B, how long to hit the ground? To find when the object hits the ground, we must solve what equation? What should I do? What's the height of the object at the moment when the object hits the ground? 0, right? What's the height of the object t seconds after it's thrown? It's this function. So to find out when the object hits the ground, I need to take this function, which measures its height, and set it equal to 0. then I will solve that equation for t, right? So this thing is the height. So I need to solve the equation height equals 0. Now, what is h of t? What is the height? Well, it's 64t minus 32t squared. So I'm solving that thing equal to 0. All right, what's the best way to solve this equation? Sure, I could use the quadratic formula, but that would be a terrible waste of time. Good, yeah, we want to factor this, right? I can't solve this by taking square roots because there is like an x term, or here it's a t term, right? I don't just have constants and squared. The quadratic formula would be a terrible waste of time because this factors really nicely. You can factor out a t. In fact, you can bring out quite a bit more than that. I'll start by factoring out a t, and then we'll have 64 minus 32t. And this is all equal to 0. Does anybody see anything else that can be factored out? Yeah, a 32 can actually come out as well. Both of these are divisible by 32. So this is 32t times 64 divided by 32 is 2. 32t divided by 32 is just t. So this is kind of the nicest way to factor this. But from either of these, it doesn't matter. You can take and set the two pieces equal to 0. And you get the two solutions. Here with 32t equals 0, I just divided both sides by 32. 0 divided by 32 is still 0. And when I set 2 minus t equal to 0, here I just added t to both sides. I know a lot of people would want to subtract 2 and then like divide by -1, but isn't it cleaner to just add the t over? So I get the two solutions, t equals 0 and t equals 2. So at time t equals 0, I'm just about to throw the thing. And at time t equals 2, it's come back to Earth. So the object hits the ground 2 seconds after it's thrown. Yeah, let's do that. Let's find the relevant domain and range, right? So as an abstract function, here, let me hold here just for a second. Is there anything anybody needs time to write? Here's the last bit. I'm going to hold here for about 5 seconds. Then we're going to talk about domains and ranges. Okay. So let's look at the graph. We found the vertex. We found the x-intercepts. Our vertex was at h was 1 and k was 32. So this, of course, is 0. I'll mark this as 1, and I'll mark this as 2. And I'll mark this up here as 32. No one can stop me. All right. So here are some points we know are on our graph. So here's my parabola. It's looking like this. This is the t-axis. The question was, what is the domain and range? This is the function 64t minus 32t squared. Is everybody comfy with how I graphed that? The times when h of t was equal to 0, those are the x-intercepts. Those were 0 and 2. And then the vertex up here, we found that together in part A. That was the point 1, comma 32. Once you have the x-intercepts and the vertex, you can graph a beautiful thing. Now, yeah, we can find two different sets of domains and ranges. The abstract function has domain and range, blah, blah, blah. The relevant domain and range for this model, for this mathematical model, are different. Yeah, relevant is a good keyword here. It's the domain and range that is relevant to the problem, right? Relevant to the real world problem that this function is supposed to be modeling. For example, if I look a half second before the ball is thrown, is the ball really going to be like 16 feet underground? No, right? Half second before the ball is thrown, it's in my pocket. It's still at height 0. So this part of the graph is not relevant to the real world problem. So I would exclude this part of the graph from the domain and range stuff if I'm looking for the relevant domain and range. Similarly over here, the ball falls, hits the ground. Does it start furiously tunneling under the earth? No, it just sits there. So this part of the graph is also not relevant to the mathematical model. The only part of the graph that's really relevant to the model is this part. But let's do the abstract domain and range first. The abstract domain, the domain for the abstract function here, meaning just thinking of this as a mathematical object, nothing to do with the real world. The domain is negative infinity to infinity. This parabola continues like this forever and ever and ever. The same is true for all polynomial functions. They always have this domain, negative infinity to infinity. The range, so the range is interesting, or at least, a little bit more interesting. Remember the game, you have to get the domain, you squish the graph down onto the x-axis, and that everything gets hit, so that's negative infinity to infinity. To find the range, you squish the graph down onto the y-axis. So if I came in here and started smooshing all these points over, this point would get smooshed to here, and everything below him would get hit. So the range for the abstract mathematical function is everything up to 32. That's negative infinity up to and including 32. If I'm talking about just the relevant domain, the domain and range associated with the model, then I'm only interested in the times that this function actually describes the behavior of the ball or the object, whatever it is that's being thrown. So like we said, the ball certainly doesn't tunnel through the earth before I throw it, and it doesn't plow into the earth after it lands. So the relevant domain here is 0 to 2. And the relevant range here, if we smush this graph onto the y-axis, paying attention only to the part of the graph that is relevant to the problem, I said our relevant domain is 0 to 2. Our relevant range is 0 to 32. the ball is never at height -2 or -1 or -5, and the ball is never above height 32. So I can try to illustrate which pieces are coming from where, a little bit more highlighter. All right. So again, when you're trying to find the abstract domain and range, it's just the smooshing game that we talked about at the very start of the semester. The domain is the set of all the x values, or in this case, t values that are on the graph. And since the parabola continues left and right infinitely far, that domain would be -infinity to infinity. All the y values on the graph, that's the range. So you imagine smooshing this whole graph down onto the y-axis. Everything below here gets hit, but nothing above 32 gets hit. So your relevant range is -infinity up to 32. Please remember, in interval notation, smaller number always goes on the left. Okay. How am I doing on time? Maybe you guys till 10:45, right? We got about 30 minutes left. Sure, Mark, what would you like to do with that? You want to solve that? Okay, yeah, let's do it. So I don't know if everybody else saw in chat, Mark put forth an equation that he would like to solve. Before I move away from this, are there any questions on this problem? Okay, here we go. Did the problem ask you to solve the equation in a particular way, Mark? Solve graphically, just solve however you want? Any silly constraints here that we should be aware of? Okay. So 2t squared equals 5t plus 3. What sort of methods do I have available? What are my options here? Can I solve this by taking square roots? Or can I hope to solve this using the method of square roots? No, you're correct. Why? Which term ruins that? Perfect. Did everybody see what Jacob said? It's the 5t term here that tells me I can't solve this by taking square roots. Because no matter what I do, if I isolate the t squared and then try to take square roots, there's going to be a t on the other side. So I won't be able to get like the square root of a number. I'll get the square root of some like function involving t's, and that's not going to tell me the solution at all. So because of this term, I need to do something else. Now the something else I would try first is factoring. So I would take this equation and pull everything to one side. That's our first step for factoring. Remember, in order for that factoring shit to work, we need to have the other side being 0. That's the only way factoring works. So like subtracting the 5t over and then factoring and setting that stuff equal to 3, that shit does not work. But what does work is pulling everything to one side. So I'll subtract the 5t over and I'll subtract the 3 over and set equal to 0. Remember, if we are going to factor, this has to be a 0. Right, that setting each factor equal to whatever only works for 0. Okay, so we've got that. My factoring tool here is going to be the AC method. So now I'm going to factor using the AC method, or at least I'm going to try. I could compute the discriminant and see if the discriminant is positive. Check if the discriminant is a perfect square. The discriminant b squared minus 4ac. Let's try this first. Check the discriminant to see if it's possible to factor. The discriminant is b squared minus 4ac. So that's negative 5 squared minus 4 copies of 2 times negative 3. So that's 25 minus, we got to follow your order of operations here. 4 times 2 times negative 3 is 4 times negative 6. So this is 25, right? 2 times negative 3 is negative 6, yep. So this will become plus 24, which is 49. So this is positive. So there are 2 real solutions. And it's a perfect square. 49 is a perfect square. So we can find them by factoring. Yay! All right, so let's factor this. Remember our rules for the discriminant. If the discriminant was negative, I would say, okay, fuck it, quadratic formula time. If the discriminant was not a perfect square, I would also say, okay, fuck it, quadratic formula time. But since the discriminant is positive, I know there's 2 real solutions. And since it's a perfect square, I know that this thing will factor nicely. So my AC method, A times C here, let's tuck all this into the side. A times C here is 2 times negative 3 is negative 6. So I need 2 numbers that multiply to negative 6 and add up to negative 5. All right, because B here is negative 5. Those are going to be negative 6 and positive 1. So I rewrite my equation, my 2 numbers are negative 6 and positive 1. So I rewrite my equation as 2t squared minus 6t plus 1t minus 3 equals 0. Minus 6t plus 1t is minus 5t. So remember my 2 special numbers? That's the game with the AC method. We have to find 2 special numbers that multiply to this and add up to this. Then we use those 2 special numbers to rewrite the middle term. So my special numbers here were negative 6 and positive 1. So I rewrite the middle term, the negative 5t, as negative 6t plus 1t. And now we factor by grouping. Yeah, I never learned this properly in high school. In high school, they taught some bullshit guess and check stuff. Nobody showed me an actual method until like Calc 1, actually. It's pretty embarrassing. But you guys are doing better. You're learning it now. So I factor by grouping now. This term and this term. I pull out as much as I possibly can from each. From the first term here, I can pull out a 2t. And what will be left is t minus 3. From the second term, I can't really pull anything out. I'm just going to think of that as I factor out a 1. And then I'm left with t minus 3. And this is all still equal to 0. The 1 here is a little bit sneaky, but does everybody understand that factoring out a 1 really does look like this? It's not anything special. 1t minus 3 is the same as 1 times parentheses t minus 3. Now, because I chose my two special numbers correctly, when I factor out as much as I can, these things will match. If the things in parentheses here don't match, that means you made a mistake. You need to go back. But here they do. I've got a t minus 3 there and a t minus 3 there. So I can factor out t minus 3. And that will leave me with 2t plus 1. Right? 2t plus 1. And then t minus 3. I write it spaced out like this so you can kind of see where everything is coming from. But you don't need to write it like that if you don't want to. This is 2t plus 1 times t minus 3 equals 0. So now we set each term equal to 0 on its own. Two t plus 1 is equal to 0. That means 2t is equal to negative 1. Subtract the 1 over. And then I divide by 2. So t is negative 1/2. T minus 3 equals 0 just means t is equal to 3. So here are my two solutions. Not so bad, right? Questions on this? Yeah, of course. All right, I think we still have probably around 15 minutes. What else would you guys like to do? What other problems are you worried about? What other stuff from the homework, if you saw it on the test, would frighten you? Okay, so Matthew has sent me something in chat here privately. The number y in thousands of women in the workforce is given by the function y equals 5.6x squared minus 18.08x plus 606.09, where x is the number of years since 1900. All right, I will write that down. While I'm writing that down, Matt, could you tell me what we want to do with this? What is the question we're hoping to answer? Y equals 5.6x squared minus 18.08x plus 606.09, where x is the number of years since 1900. We want to find y when x is 33, okay? And explain what it means. What else do we want to do? That's it. Okay, cool. So, who can help me out? Well, let's just do it, right? So they say find y when x is 33. Well, here's the relationship between y and x. So if I want to find y when x is 33, I take this expression and I substitute in 33 for x. So when x equals 33, y is going to be, and I encourage you to write things like this down before putting them in the calculator. Takes the, oops, sorry, shit, like this, right? Like here's me making a mistake. 18. Y equals 5.6 times 33 squared minus 18.08 times 33 plus 606.09. So write these things down, then put them in the calculator. That way you can go back and check your work. And you can see, what you did at each step. Let's turn this guy on. Let's clear out of this. I need 5.6 times the square of 33. I'm going to do one term at a time. Well, nah, because we don't want to have to round each term separately. So here's the first part. Just make sure that you're using parentheses carefully. The inside of a function, the thing you're plugging in, always needs to be in parentheses. So there's that first term. I'll put the whole thing in here. It's okay. Plus 18.08 times 33. There's the second term. Whoop, and you see I made a little mistake there. I put a plus where there should be a minus. Go slow, check our work. Thank you. Yeah, Mark caught that. I appreciate it. All right. And then plus 606.09. Okay. So this is giving me 6,107.85. So when x is equal to 33, y is equal to 6,107.85. Now, the more challenging thing here is to interpret, right? So what do they mean? What do they want us to say? What is the meaning? What is y measuring? Well, y measures the number of women in the workplace, right? The number of women in thousands. So this times 1,000 is the number of women in the workforce. Yeah. So there are, or in this case, were 6,107.85 thousand women in the workforce. In which year? In the year what? Yeah, I'd be happy to. Good, Kendra. Yeah, 1933. Remember, X is the number of years since 1900. So if I'm plugging in 33 for X, that would be in the year 1900 plus 33, which is 1933. Right? X is the number of years since 1900. So when X is equal to 33, we're talking about 33 years after 1900 or 1933. Now we should really figure out what this number is. If there's this many thousands of women, then we need to multiply this number by 1,000, which is just going to have the effect of skipping the decimal place over. So I would say this in one sentence as in 1933, there were 6,107,850 6,107,850 women in the workplace or workforce. That would be a good one-sentence answer here. Now they also ask us to find how many women were in the workforce in 2030. So we're going to need to plug in a different X value for that. I'll do that in a second. Mark asks, could we graph and see where this intersected at X equals 33? Kind of, yeah. So let me go ahead and feed this function here. We've got 5.6x. The catch is that it's kind of hard to read a graph like this perfectly. We can make approximations, but I'll show you a neat tool in the calculator here. Minus, did I use the right symbol there? I don't think I did. Minus 18.08 x plus 606.09. And we can look at the graph. This is going to be a very different looking graph than the one we graphed a second ago. So let me fiddle with my settings here. I always like to start at minus 10, 10, scales 1, minus 10. Oh, shit. Minus, no, go away, fuck you. No, die, abort. Oh, fuck. Still not quite used to this emulator. All right. 5.6 x squared minus 18 6.9. Now remember what we learned. We learned that the number c is always the y-intercept. So this thing is starting all the way up at 600. So I need to make my y max at least 600. Let me change this to like 1000. Y min negative 10 is fine. X min negative 10 is okay. Let's set my X max to like 100. And just see what we get. All right. So here's a little picture. I need to make my Y max way bigger, and I can bring my X max in a little bit. I don't need to go all the way up to 100. Let's go up to 50. And let's make this like 10,000. There we go. Now you can play around with the trace function here. All right, and we can march on over close to 33. And we're seeing something pretty close to what we got. We got 6107, and this is showing 6250, but X isn't exactly 33 here. It's 33.4, and there's 32.7. Now, if you want to get a little bit more specific, we would hit second and graph to pull up a table. And now I really can scroll to any particular X value I want. Right, this is just like a table of X and Y values that we made by hand when we first graphed Y equals X squared. And here you see they're rounding to one decimal place in the Y values, but you see this is what we got, right? This agrees with what we got if you round to the one decimal place. And then down here, they give you the exact value, or at least as close as they can. So the table feature on your calculator can be useful. And again, the way you get to the table, wherever you are, you just hit second and graph, and that will pull up your table. You can change the table settings by hitting second and window. Okay, you can say where you want to start the table and how big a step you want each scroll down to go. All right. There were two other things we wanted to do with this before we bounce, so let me try to get at least one of those. So the question mark, can we look at the graph and see where it intersects at X equals 33? Kind of, but the table would be better than the graph for that. How do you solve when it gives you the number of women in the workforce and asks you for a year? We would need to solve the corresponding equation. So how many women do we want to solve for? What's the number of women in the workforce we would like to sort out the year for? And say, in what year will there be blank women? You guys pick the blank. In what year will there be 2020 women? Or, so that's a different question, right? How many women will there be in 2020? So to answer a question like the first one here, in what year will there be blank number of women? You would need to set this equal to that number of women and then solve. And yeah, to do that, you would subtract the constant over and use the quadratic formula. To answer the second question here, you just plug in 2020 for x. But 2020 isn't actually the thing you're going to plug in. You have to figure out the x value that corresponds to 2020. So in 2020, the variable x is how many years after 1900? Well, I would just take 2020 minus 1900. And you're going to get 120. So we would plug in x equals 120. There will be y equals 5.6 times 120 squared minus 18.08 times 120 plus 606.09. Is everybody comfy with why the year 2020 corresponds to the x value 120? Because x is the number of years since 1900. To go from year 1900 to the year 2020, you got to jump ahead by 120 years. So we can go ahead and do this computation. Get out of here. We can go ahead and do the computation. 5.6 times 120 squared. And again, we always put the inputs in parentheses, like this, minus 18.08 times 120 plus 606.09. And here we're getting 79,076.49. And remember, this is being measured in thousands. So if I want the actual number, I need to multiply this by 1,000. And that gives us this. All right. So we have run out of time for the class, so I'm not going to go ahead and be able to solve that last bit. But yeah, if you want to know when there are some number of women in the workforce, say, I don't know, 25,000 or 2.5 million, you would set this equal to that. We would need to solve 5.6x squared minus 18.08x plus 606.09 equals 25,000. You'd have to solve this equation, and you would do that with the quadratic formula, right? You would pull everything over. You would have to subtract the 25,000 from both sides to make this a 0. That would combine with this, and then use the quadratic formula. The activity for today, I wanted to do an in-class activity, but I'm happier to solve problems that you guys want to solve. So I don't have an issue with us not doing the activity. I'm going to go ahead and give credit for the activity just based on your participation in class today. So everybody who showed up here today will get credit for the activity, but the project, I do need you guys to do. All right. So just to be clear on this, come here to the assignments, go to project 1, download, follow this link to download project 1. That's the pizza thing. Print that paper and make sure you come back here to Canvas and submit your scan of that completed project by the end of the day on the day of the test, which is next week. Everybody who's here today is going to get credit for the activity. You don't have to worry about the activity, but it wouldn't hurt you to go ahead and do the activity too. It would be very good practice, right? Obviously, I write your tests, I write the activities and projects. So if you're looking for extra review material, coming in here and doing what was intended to be today's in-class activity would be a wise move. If you don't have access to a printer for the project, yes, you can write everything out on your own paper. I would prefer if you printed and wrote everything out on the print. I would prefer if you printed this out and actually wrote on this and then scanned that. But if you don't have a printer, you can write everything out yourself. Just make sure that you scan and submit the full solutions by the end of the day next Tuesday. And please don't forget your name. Names are important. Other stuff for the exam, please, 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 please read the announcement here that has the instructions. All right. I really don't want anybody to have any trouble with the test. It's really important that you follow these instructions exactly on the day of the test. All right. Reading this and following these instructions will make the test go smooth. And you want that. You don't want to be panicked about some other bullshit having to do with Zoom or honor lock on the day of the test because it's going to distract you. So please make sure that you've got Zoom installed on your phone. Make sure you know how to join a Zoom meeting on your phone. You're going to need to set up your phone so that I can see your desk and your hands on Zoom. Make sure you have Chrome installed on your laptop, and make sure that you have Honor Lock installed to Chrome. Make sure everything is up to date. And then please read these instructions. Make sure you follow these instructions. The rules for like writing out your written work are very important because that's how I'm going to grade your test. It's all based on the written work. That's where all the credit for the free response problems come from. So please do that, do it carefully. If you guys have any questions, you can come see me in office hours, or you can send me a Canvas message. Again, I really encourage you to come by office hours. It's a great place to ask for problems, ask for help with anything. Happy to do it. That's it. That's all from me for today. Any burning questions before I let you guys go? All right, I hope you guys have a lovely rest of your day. If you do have questions, again, you can come by my office hour. I have an office hour today, starting at 11 to 12. And then you can also send me Canvas messages. I'm happy to set up an extra office hour if you need to. I will be moving on Saturday. It's going to be a little bit hectic, so Saturday's not a good day, but maybe Sunday if you need an extra office hour, just reach out to me and I'll work with you. Same for any of the old homework. Please get all the old homeworks and quizzes knocked out. Let's be good about this shit. Before the test, you should have everything from homework 1 through homework 9 and quiz 1 through quiz 3 done in my math lab. Don't forget the test review. All righty. Take care, guys, and that is it. I'll see you all on Tuesday for the test.